Hi, in this virtual problem solving session, I'm going to walk you through some of the important steps for our 3 homework problems on power screws. So problem 1, double thread power screw with Acme threads has an input power of 4 kilowatts at a speed of 1.5 revolutions per second. The screw has a major diameter of 45 millimeters and a pitch of 9 millimeters. The frictional coefficients are 0.15 for both the threads and the collar, with the collar radius of 55 millimeters. Find the axial resisting load F. In other words, the axial force that is generated from the input torque. So the first step, or how I went about it, find the input torque from power and speed. So we've seen this relationship a lot, power equals torque times speed. So your first challenge is to look up the SI units for kilowatts and work through the necessary conversions to get torque in terms of Newton meters. So you have the power delivered by the motor and you have the speed. So how can you find the torque? And it's a bit of just juggling some units. So that's the first part. So that will give you the overall torque or the total torque provided. So next, write expression for input torque as a function of F. This part's pretty interesting, so you'll definitely need your analysis tool. So we have TR and TC, so the torque required to raise the load, in other words, provide the resisting axial force F, and then TC, the collar friction, the torque required to overcome the collar friction. So the knowns that you have the lead, the mean diameter, secant alpha, the friction coefficients, and the mean collar diameter. So you're going to plug all of these values into your analysis tool along with F equals 1. And what that will give you is TR equals some number times F, and TC equals some number Y times F. So here X and Y will be numbers, and that's based on inputting 1 for F and all of your known inputs. So then what you do, you have your input torque total provided by the motor. So you can set that equal to the torque required to raise the load and overcome collar friction, and that's going to allow you to solve for F. And that's really the gist of this problem. And I'm having you do this problem first because you're going to use this same process for problem number 3. Problem 2, I like this problem because it incorporates some of what we learned about gears. The press shown has a rated press load of 6,000 pounds, so you can think of that as the pressing capacity between the bottom and this top plate. The single thread twin screws, so meaning that they're identical screws but they're single thread, have square threads, a major diameter of 2.5 inches and a pitch of 1/3 inch. Coefficients of friction are 0.06 for the threads and 0.09 for the collar bearings. Collar diameters are 3.75 inches. You can see the collars are down at the bottom marked. The gears have a total speed reduction of 48 to 1, and the full motor speed is 1,650 RPM. So starting from the top, we have 1,650 RPM, and we have a 48 to 1 speed reduction. So from that, you can figure out the RPM of the screws. And then given the lead, what is the linear velocity of the press head? Next, since you have a rated press load of 6,000 pounds, how much pressing force does each screw need to provide? And then from there, what torque is required to generate the needed press force? And remember, just like we've seen in the previous problem, some of the input torque will be used up to overcome collar friction. So this is the torque that the motor has to provide, but remember it has to power 2 screws, and it also has a 95% efficiency, meaning that about 5% of the power provided by the motor is going to be lost. So for this problem, the biggest hint is to remember the conversion. 1 horsepower equals 550 pound-foot per second. And then for grading consistency, take the 95% efficiency into account when specifying the horsepower of the motor. Problem 3 will probably take the most amount of time. So we have a screw clamp or a C-clamp shown. A force of 45 newtons is applied at the end of this handle here, 8 centimeters from the screw center line. The handle itself is 9 millimeters and it's made of cold-drawn AISI 1015 steel. The single thread screw is M20 by 2.5 and is 10 centimeters long overall. Assume a friction coefficient of 0.12 for the threads and 0.15 for the collar. The mean collar diameter So down here, DC is 2 centimeters, and the maximum possible length of the screw in the clamping region, so from here to here, is 6 centimeters. So first step, find the input torque. So this is essentially the screw torque generated. You know the force applied on the handle, you know the distance to the screw center line, that should not be difficult. And then follow the same process you did for problem 1 to write a function for T in terms of F, then solve for F, the clamping force, making sure to account for both the torque required to overcome collar friction as well as to provide the clamping force. So you have all the inputs you need for this. You have an M20 by 2.5 single thread screw, like I said. So from there you can find the lead and the mean diameter, and then you're also given the collar diameter and the coefficient of friction for the collar. So the next part is back to ME 328 for column buckling. So this next question is, what would be the critical axial load, PCR, that would cause the screw to buckle if it were clamped down on something, and you're considering the column to be the 6 centimeters, which is the length of the screw within this clamping region. So spoiler alert, it would be a very high load to cause the screw to buckle, but it's still interesting and I think good review of 328 to go through the steps. So the first thing you're going to have to determine, is this an Euler or a long column, or is it a Johnson, a medium column? So you can go back to chapter 417 in Shigley, although I've provided the highlights here. So Euler columns, the critical load is C pi squared E over the slenderness ratio squared. So C is the end condition constant. You have to look up what that is. You're given pinned fixed column ends as your assumption, E modulus of elasticity, I moment of inertia, L over K. So the slenderness ratio is a measure of how long and skinny a column is. So L is the length of the column, in our case, the region of the screw that's in the clamped zone, and K is the radius of gyration, and that's equal to the square root of the moment of inertia divided by the area. For these calculations, use the pitch diameter. Johnson columns, PCR over A equals the yield strength minus the yield strength divided by 2 times the slenderness ratio, that whole quantity squared, times 1 over CE. So no new inputs other than SY, the yield strength. You already know what that is. And you can look that up from the material specifications in the back of the book. And then the next question, how do we know whether to use Euler or Johnson for our PCR calculation? So remember, you calculated a reference slenderness ratio, and you used that reference slenderness ratio to compare to the actual slenderness ratio to determine if you had an Euler or a Johnson column. So your reference slenderness ratio, in the book it's called L over K1, and that was always a little bit weird to me when I taught 328, so I would just say reference equals 2 pi squared CE over SY to the 1/2 power. So that's your reference value. And if your actual slenderness ratio is less than or equal to the reference slenderness ratio, use Johnson column. Otherwise, it's long and skinny enough to be considered an Euler column. So you use a different equation for PCR. So you'll use either Euler or Johnson equation to find PCR. That becomes your F, and you need to figure out what force on the handle would induce this F. So here you're just going to get a little bit creative with your analysis tool, but I think you'll figure it out. Then the question becomes, do you think you could realistically transmit this high handle force to the screw, so a high enough handle force that would generate this critical buckling load? Would perhaps the handle fail due to direct shear first, or maybe fail due to bending? And you have to check both of these scenarios and justify your answer quantitatively. So our formula for direct shear, tau equals V over A, and you're going to compare to tau allow. And as a quick rule of thumb, you can use 75% of the yield strength as your allowable shear stress for this ductile material. And then again, when calculating A, I would use the pitch diameter. And then for bending, sigma equals MC over I. And you're going to compare to sigma allow. In this case, you have a ductile material, so your sigma allow would be SY. And then what is the expected mode of failure? Lastly is just looking at the cover sheet quickly. I didn't provide a ton of space, so show work here to justify either Euler or Johnson column. So you're just going to show the most important points so that the the comparison process, but your analysis tool should actually show your work. So no surprises, in a couple weeks when we have our final exam, you will have a column buckling type problem with power screws. So it would be to your advantage to make sure that you have it all in your analysis tool now. All right, that's it. Thanks for watching.